anyways, be prepared. Tomorrow again I will ask about feedback, okay? Okay, so let's get started, okay? So we'll talk about mechanical properties. Okay, so when you talk about mechanical properties, what are some of the properties that will come to your mind? I talked about these many times, here and there, but stress strain, exactly. So that's where we start. What's Young's modulus? What else? Hardness. It's very good. Yeah. Brittleness. Yeah. What is it? Cohesiveness. It's not a mechanical property. Yeah, but ductility. Very good. Elasticity. What's it? Chewiness. Chewiness. Maybe. Yeah. Those. Shear modulus. Yeah. Yeah, chewiness, I'm not sure. Is that a mechanical property? I don't talk about that in the class, okay, at least. So maybe it's more in food, right? Yeah, so. Poisson's ratio, what's that? Okay, yeah, that's what I don't know, so might be. Okay. Anything else? Okay, I believe, most of it, most of the properties you all covered, okay? So one of the challenges, when we talk about, biological materials at least, they are not isotropic, right? So, but if you are talking about metals and some other, manufactured components, commonly they are isotropic, right? So, if you go in any direction, the properties are same, okay? But for biological materials, mostly anisotropic, right? The properties change based on where you measure. Just for an example, you might know about different types of corn, right? You all know popcorn, yellow dent corn, high waxy, high waxy corn, high amylose corn, etc., etc., right? So their build of starch inside those corn means maize, okay? You all know, right? So depending on this type of starch, their properties will also be different, right? So their mechanical properties, how the starch is intact inside the kernel will change almost all their mechanical behavior, okay? Even optical properties, etc., okay? So again, for any powders or any granular materials, the properties will change based on orientation, right? If you take a maize kernel, okay, so one side it will be germ, right? The other side it will be more, starchy and protein component, right? So if you measure the properties on one side, it might be different than the other side, right? So properties always differ, and again, other effects from shapes will also play a role. Composition, surface composition will also play a role when it comes to mechanical properties. Okay? But as said, the most basic stuff that we calculate is stress and strain, right? Stress we calculate from force over area. Okay, there are two stresses, right? One is true stress and engineering stress, right? So true stress is divided by the current area. That means when you are compressing or pulling, for example, you take a plastic sheet and pull, it slowly expands, right? But the cross-sectional area is also changing, right? It becomes thinner at the middle, right? So that's what we calculate in true stress. That means we account for the change in cross-sectional area. But engineering stress is you take the original area that you are measuring, and that's it. You will not change the cross-sectional area for calculations, right? Same holds good for strain. Okay, so true strain, again, change in deformation, with the corresponding change in cross-sectional area. But engineering strain is, we commonly don't take the, change in, cross-sectional area during the mechanical testing or mechanical process into those calculations. Okay, so calculating engineering stress and strain is easy, right? You know the cross-sectional area, you know the force, you do that, right? But for calculating true strain and true stress, it will be a little challenging. Okay, true strain, you can use some video recordings. There are some LVDT, what's a linearly variable dynamic, I think dynamic testing instrument. That is a displacement. Yeah, that's very good. Yeah, displacement. Yeah, transducer, right? Yeah, LVDT. can use, to measure the change in cross-sectional area and, get the true strain. Okay. So when you take a typical, tensile test means you're pulling it. Okay. So what happens is, again, you can relate to pulling a plastic sheet, right? So what happens, it goes to elastic deformation, plastic deformation. At one point it breaks, right? So initial, when at smaller loads, when you pull that plastic sheet also, it comes back to its original position, right? So that's the elastic deformation. All the, you know, strength, whatever it lost during those, pulling will be regained by the material, right? But when you cross that yield point, okay, or yield strength, okay, there will be more change in cross-sectional area. That means there will be more, again, change in the material behavior, where you will not regain it back. When you lose the, when you remove the stress, you will not regain back its original properties. Okay, that's the plastic deformation, right? Right, you all know about this, right? At least most of you. Elastic deformation, plastic deformation, right? So when you keep on, increasing the stress, and again, you can imagine, pulling a plastic sheet. At one point, it forms a small neck, right, where it starts to break, right? So there will be an onset of necking, and then finally it gives up. Okay, you can easily relate, right? You would have noticed, right, when you are tearing something or like pulling something apart. Okay. So this is, again, this is a process when we go, we see when you are applying, a tensile load, okay, or pulling it apart. But if you are applying a compression, load, general, this is a compression, yeah. So you might not see a necking phenomena, right? So when you are, instead of pulling it, when you are compressing it, you may not see a necking phenomena. It just breaks. Okay, so it goes through plastic deformation, and finally it fractures. Okay, so those two different types of tests will be a little different. Okay, compression and tensile testing. Okay, but still it goes through some elastic deformation, plastic deformation, etc. Okay. So, ductile behavior, again, there will be significant plastic deformation in comparing a plastic sheet, right? So when you're applying some tensile load, it keeps on pulling until it breaks, right? But if it's brittle, what happens? It breaks suddenly, right? Like comparing a plastic sheet to a piece of paper. When you pull a piece of paper, it like suddenly breaks, right? So that's what, again, brittle behavior, almost the fracture strength and the yield point will be almost same. When you cross that, elastic limit, it breaks. Okay. So and we can, get this relationship from Hooke's law. Again, Hooke's law, you all know about that, we use in spring constants, right? Or getting those spring values. So stress is directly proportional to the strain, and the proportionality constant is the Young's modulus, okay, or the elastic modulus value. Most commonly used for linearly elastic material. So if you have some odd, behavior, odd, relationship between stress and strain, you might not be able to use this Hooke's law. That's why it makes it very difficult to measure Young's modulus for biological materials. The relationship is not linear. Again, yield strength, so stress at which it starts, breaking, and there will be more plastic deformation. That's a yield strength. Again, fracture strength, the sample at which, the load at which it breaks. Okay. So first property, again, Young's modulus, right? Young's modulus, we talked about, it's a relationship between stress and strain. Again, very commonly used to, again, characterize the resistance to elastic deformation. Okay. So we use that linear part in that, stress strain relationship. So we will not use the nonlinear part, just the linear part, and get the, relation between stress and strain, and get the Young's modulus, or obtain the Young's modulus value. Okay. And then again, with smaller E value, then, they deflect elastically to a greater degree. That means if it's a spring, the elastic modulus will be low, but if it's a hard material like compact or something, their elastic modulus will be low. Okay. Okay. So, just quickly, as I just said, if it's a lighter material, then the elastic modulus usually low, and then, again, the values to it's for mostly pharmaceutical stuff, right? So there are, again, elastic modulus, it's a material property, right? So the temperature, the humidity, the conditions at which the samples are will affect this elastic modulus values, including, how we prepared the compact. Like what strain rate we use to prepare a compact will also influence this, elastic method. Loading rate definitely, in the strain rate, testing method, etc., etc. Okay. But in general, you might remember the Spriggs equation that we talked about yesterday, right? That we used to get, extrapolated value, right? So one of the major challenges, again, extrapolation to zero, property value, okay? So that will give large errors, okay? So mathematically defining this is little challenging, okay? So humidity also plays a larger role, right? I will not go into those theory. Then again, usually presence of water, loosens those, bonds, stronger, mechanical bonds between the particles within the compact or any material, and then kind of affects the overall mechanical strength and influence the, Young's modulus value. Poisson's ratio. So Poisson's ratio is the relationship between lateral and longitudinal strain. Okay, so lateral, again, how much material moves on sideways or changes on the sideways to overall movement on the lengthwise direction. Okay. So if you take that ratio, you get the, Poisson's ratio. So mostly incompressible material 0.5, it's highly porous material like cork, it's usually 0. Okay. But you might see for some material like polymer foams, etc., you might see a negative value too. So when you pull, that might expand on the lateral direction. That gives a negative value, okay, especially for foam materials. Shear modulus, again, that's a ratio between the shear stress and the shear strain. Okay, that gives the, shear modulus. So it comes into play when you're, flow of powders. Okay, so you calculate shear stress, right? Same thing, you can calculate the shear strain, right? The strain needed to make the powder move or powder flow, right? So you get those two properties and then get the shear modulus. Again, there are relationship that relates to Poisson's ratio, Poisson's ratio and elastic modulus to the, shear modulus. I'm not going into the, derivation of this relationship, but this is simple formulas that you can, relate them. So if you know two of these, you can find the other one. Okay. And as the picture indicates, it's from shearing, one layer moving over the other layer. Okay. So bulk modulus mainly when, compressing materials. Okay. So the change in pressure and the change in volume. So when you are compressing a material uniformly from all 360, angles, so it compresses in, volume. That change in volume over applied pressure is the bulk modulus. Okay. So again, it's in negative direction. So, you might see, negative values. For incompressible material, usually it's high in negative. For easily compressible material, it's low negative values. Okay. Modulus of resilience, and from based on the elastic energy. So you take the area under the curve till it behaves an elastic solid. Okay, so that's the, modulus of resilience. Okay. So if you take the stress and strain at this point, that's a modulus of elasticity. But if you take the area, that's a modulus of resilience. Okay. So that gives, how much energy it loses and reabsorbs when you are applying some stress and strain. Okay. So it gives that calculation of energy lost during this. Okay. So toughness modulus is until breakage. So you take the area under the stress strain curve until it breaks. So it gives the toughness of the material, right? So how much energy it takes to break any material. Okay, it could be both for compression and also for tensile measurements. Okay. Okay, again, plastic. I'll go back. So any, can you give some examples of these applications? We talk about examples, right? You all wanted more examples, right? So where do we apply this toughness modulus? Any examples that you can think of? Why do we have to characterize toughness modulus?
To determine like up to what load it can be stable if you want to.
Okay, so exactly. So where do we see those applications? Where do we see those applications?
To differentiate between ductile and brittle, if the modulus of resilience and toughness are same, we can say that it is brittle.
Yeah.
And otherwise it's ductile.
Okay, sure.
Cracking some material.
Cracking. So very commonly, you can use this for milling purposes. Okay, that's a very common example. Okay, so how much energy it takes to mill or break into pieces? Because when you exceed this toughness modulus, then definitely it breaks, right? So it losing, the same amount of energy that will needed to break the material, right? So same thing for, modulus of resilience too. Okay, any examples of where we can apply modulus of resilience? You would notice this almost every day when you go for shopping for fruits and vegetables, this modulus of resilience.
In polybags.
What's that?
In polybags.
Not poly bags, maybe, yeah, poly bags too, how long you can hold the bag before it breaks, right? So that one. But can you think about any example on fruits and vegetables?
So like how we can keep the fruits and vegetables so that it will not get damaged.
Yeah.
It can help in that.
So exactly for that, so sometimes when you buy apples, you might see some brown spot, right? So how does that brown spot is occurring? From damage, right? Some impact damage, right? Or some kind of abrasive damage, right? So, but if the load that is applied on the fruit during handling is less than this, modulus of resilience, then there will not be any brown spots. But if the load exceeds, or if the energy exceeds that you apply on the surface of the fruit or vegetable, then you will see brown spots. Again, based on the energy that you apply, then the area will also increase. Okay. So again, I'm not giving applications or example, but you can relate to almost everyday thing that we do. Okay, all these properties. Okay. So plastic work is mostly for cyclic compression. Okay, so for example, I'm compressing this material like 100 times. Okay, so when it when you keep on compressing, when it exceeds the elastic limit, I lose some plasticity, right? I lose some energy. So the difference between the compression and loading and unloading curve, after it exceeds the plastic limit, is called the plastic work. Okay. So amount of energy or energy that loses in that the material loses between multiple or cyclical compression loads or tensile loads. Okay. So what example you can think of where we apply this?
जैसे बीम होता है ना सर, बीम पे कंटिन्यूसली लोड लगता है, वो बैंड हो जाता है बीच में से.
Yeah, so I'm talking about food materials. Okay, beam. Okay, and food, fruits, vegetables, grains. What example that you can think of? Cyclic loading.
So
So
gels or
yeah, gels. Yeah, maybe what's that?
दो सर.
Dough. So what do dough? What do what? Uh,
Stable.
what's that?
Permanently change हो जाता है.
Yeah, that's more rheologic work than more plastic work. You know, so we are changing the property itself, right, of the components. Well, that's a good guess though. Okay. So we talked about apples, right, or some grains, right? So can you think of some examples where we can apply this plastic work to improve the safety and handling or improve the quality of materials? No? Go ahead, yeah, tell, Uh-huh. Yeah, grapes, what happens in grapes? Don't tell while eating, chewing, there will be plastic work. Yes, there will be plastic work, okay.
Cherries also, sir, we can do.
So, all fruits, vegetables, grains, what happens, when you are shipping and handling, there will be cyclic loading, right? There will be load, unloading, when you're shipping, when you're handling, when you're rolling the materials, when you're harvesting, there will be load, then you keep the material idle, then you pack it and then ship it, then there will be load on the fruits and vegetables, right? So there will be always cyclic loading and unloading, right? So depending on the plastic work, again, it can change the damage level in those fruits and vegetables, okay? Or even grains too. Grains, we handle multiple times, right? When it flows from farmer's field to a grain storage, FCA godown or something, it's handled multiple times, right? So it goes through those cyclic loading, okay? So again, hardness, it's the surface resistance to plastic deformation, okay. Mostly we use this when it comes to abrasive damage, like for example on surface of fruits again, if you wanted to avoid avoid abrasive damage, the load should be lower than the hardness limit of the surface of the materials, okay. Again, increasing hardness implies an increase or higher resistance to permanent damage, right. So you might know some stone fruits, it's they're very resistant to cut or abrasive damage, right. But if the fruits are soft like grapes or apples, they easily damage, right. Again, very similar to the other properties, hardness is not an individual property, but depends on other values like Young's modulus, yield strength, and etc. Composition, etc. that influence this hardness. Okay. Couple of hardness testers. This is for compacts. Okay. Mostly used for compacts. When you make compacts, you can compacts, metals, steel materials, material manufacturing, etc. They use these hardness testers. Okay. Again, only minor difference here, in the Brinell hardness measurement, they make a spherical indent. Okay. So they make a spherical indent on the surface of the compact, and then based on the measurement of that permanent deformation and the other force and other dimensions, you calculate the hardness of the material. Okay. Simple formula, simple calculation again. The Vickers hardness is little different. It makes a diamond shape indent. Okay. Just their stress calculations are little different for a round indent or round hole and a diamond hole. So that's why the values, the calculations will be little different in these two methods. But again, both are most commonly used for testing the hardness of compacts. Okay. Fracture energy, again, fracture will depend on the stress concentrations. So again, if you have a corner or if you have some cracks on the surface of the materials, there will be higher stress concentration around that cracks and around on the surface. Okay. So that will be the highest probability or place where it starts breaking. Okay. So that's what we characterize using fracture test. I'm just quickly going through. Okay, creep. Creep again, it's a progressive deformation. That means you apply some stress, okay, and keep the stress constant, okay, and you monitor the change in strain, okay, how it's deforming, okay. So that's called creep. Over a period of time, the strain might change. There will be primary, secondary, and tertiary creep. But if it exceeds that creep limit, there will be a fracture. Okay, or the material, there will be more plastic deformation. Okay. So it's also highly, again, temperature dependent mostly for compacts and other materials, manufactured materials. But again, it depends on other parameters too, thickness, composition, etc. Okay. So can you give one application from fruits and vegetables on where do we apply creep to know their behavior? It's again, think about we are applying the stress, keeping the stress constant, and we are worried about the strain, change in strain or the dimensions. Okay. We think of one application. Where it will be useful to know the creep behavior. Think about fruits and vegetables, okay? One clue. Yeah, watermelon where? How exactly?
Where we stack the watermelon.
Exactly. So stacking not only watermelon, any fruits and vegetables, when you stack, in containers or in packages, what we are doing is the load is constant, right? The stress is constant. We are not changing the stress. But, it can deform strain, it can change in dimensions, right? Watermelon will be a little difficult. You need lots of pressure, but, other,
They stack too much.
yeah, but still their hardness, surface hardness is very high. If you like stack till a tree level or more than a tree level, then you might see those creep behavior. But for other fruits and vegetables, apples, you take any apple, oranges, you see those effect from creep or constant stress condition. So same, almost opposite, similar concept is stress relaxation. So you compress a material and you keep the strain constant, and you measure how much it's losing, in stress, how much it's adjusting itself to that condition. Okay. If it cannot adjust to that condition, then it will fail. There will be more plastic deformation. But if it can relax to its original position, then the material can be within those elastic limits. Okay. So that's again stress relaxation. There are some examples here. It depends on the material properties. So some relax immediately. Some materials will take a lot of time to relax. Okay. For example, watermelon could relax immediately, but for apples and softer fruits, it might take time for them to relax. Okay. Again, these all properties will come into play if you are handling materials. Okay. So wear, again, we talked about wear and friction, right? So when one material passes over the other surface, then one surface could lose some components, right, due to wear. So it's very significant again during handling of materials. Maybe for milling, wear is desirable because you want to break the particles into smaller pieces. But for handling and shipping, it's not desirable, right? You want to have the material intact, right? So again, it's very similar to like, what we talked in friction. So there will be multiple asperities contact between the surfaces, and when it's moving over, one surface is moving over the other surface, there will be stick-slip motion, right? For example, in these asperities, it sticks, and when it's moving here, it's slipping, right? There is no contact between the materials. So again, there are instruments that can calculate the wear. One is, again, we talked about tribometer, right? Tribology testing is common to get the wear strength of those materials. For compact, again, it's a conical asperity tester is common, mainly for pharmaceutical industry. But there are models. If you are again using DEM modeling for breakage, etc., then you will be using some models to calculate that wear. One common model is the Archer-Beard model. Based on the force that you apply, you can calculate the volume of material lost from the surface. Okay. So again, it's again easy calculation. Edge chipping, it's very common in pharma, but I didn't change. But if you're interested, edge chipping is, sometimes when you open tablets, you might see some edges are not uniform, right? It's a big problem in pharmaceutical industry, edge chipping, losing on from the surface. But if you're in the future, if you are going to compact, powders, then this will be a problem too. Okay. Do you know why edge chipping occurs? Any thoughts, any guess? Due to non-uniform stress on the edges, there will be higher stress, right? And again, if you do not lubricate well the compaction process, then you lose materials. Okay. Okay. So yeah, some standards here. I'll quickly go through the compact testing procedure. Now, for most of these properties, we use this uniaxial compression machine or the Instron testing machine that can get most of the mechanical properties. The basic thing we all know, right? So the force and stress and strain, right? That we can get from these uniaxial compression machines. Okay. Skip this. So hardness in general, it's called the Brazilian test. So it's again mostly for compacts. Okay, you compress the material, and based on the type of fracture, you can assess what type of forces were acting during those fracture. Okay, if it vertically cuts, it's normal tensile fracture. Shear and compression, triple cleft, again most commonly used in pharma industry, based on the forces, how it breaks into pieces. Okay, and very useful when you come to packaging and shipping. At what type of forces these will break. So tensile testing. So we again this is again we assume that the forces acting on all the sides are equal. So you compress the material. Okay, so the test name says tensile testing, right? Tensile is pulling, right? But how are we applying force? We're applying compression, right? So we assume that the forces on both directions, both compression and tensile forces are equal. Okay, but it doesn't happen all the time. But it's a major assumption that we make, so that it's easier to measure tensile strength of compacts. For sheets, plastic sheets, paper, simple materials, you can just pull them and you can measure the tensile strength, right? But for compacts, hard materials, you cannot pull them, right? So it's very difficult to measure tensile testing. So they develop these methods, like using compression, you measure the tensile forces. Okay. Same application, for testing the tensile forces using 3-point bending. I'm not sure if any of you use 3-point bending. So 3-point bending. So you keep the compactor material on surface, 2 points where it's held on the top of those 2 contacts. Okay. So these are the contacts where the compact or any material is kept, and then you measure apply force at the center between those 2 holding holding rods or holding things. You apply force, and you assume that the compression force applied on the top is equal as the tensile force that's occurring on the bottom. Because the force here is compression, right? But here it's tensile, right? It's extending, it's tensile force, right? So we assume that the compression force applying on the top is equal to the tensile force occurring at the bottom. Okay. So using that assumptions, we calculate the tensile behavior of the material. Okay. Friability, if you're working on compacts, is common. You put some compacts into a friability tester and rotate it for some time. Very common in compacts also, granules, like fertilizer granules or any type of granules. You can see how much material we lose during handling and shipping. So you rotate for some amount of time, and from the amount of sample lost during that rotation, then you calculate the friability. So this again tribometer testing, pin on disc, same as tribology. So you hold the material, and using a pin or disc, you apply the force on top of the material, and from the forces you calculate the other properties, tensile strength mostly, or amount of friction, etc. Okay, so that's it. Oh, you asked my contact, right? So that's my email ID. You can try. So okay, so we have about We have some time for questions from any topic, not only this.
Sir, could you explain me about the real modeling?
What's it?